there, folks. How we doing today? Good morning. Today we're going to talk about streams for a little bit. There may be a few slides that I'm going to edit out of this. All right, we're kind of doing a condensed version this semester. But there's still a handful of terms we want you to get. So, if you pre-printed out the handouts, you might just want, when I skip a slide or something, feel free to put a big old X on it. So, surface water drainage systems. Really kind of unglorified definition there. It cuts right to the chase. And, you could be even more crude and say it's a ditch with water in it. And in the end, that's really all they are. And their purpose is to drain the surface, or more so. Not that they necessarily have a purpose in life, but they are because of drainage at the surface. So remember, this falls under, if we go back and think about the water cycle, that fork in the road where we talked about the water does one or two things. It percolates into the earth and becomes groundwater, or it stays at the surface as runoff. This here's runoff. Also, by now, you've heard plenty of times that we use the term stream for just about any ditch that's full of water. Doesn't matter how big it is. And that's because, whether you want to say it's colloquial, regional, whatever, we've got a whole bunch of different words that we use when we're talking about streams. And for the most part, they imply size, girth, width, if you would. And of course, any number of them come to mind: creek, or my favorite pronunciation of it, crick, river, brook. Okay, we could go on and on and on. Each one of you might mean something slightly different. But I'd hazard to say, if I made some sort of weird multiple choice question wherein I had you guys arrange something, a list of these words due to size. That's my coffee spilling, isn't it? Yes, it is. Arranged it due to size, that you guys would probably get it right. I'm going to pause this here. If I could get the stupid mouse. Where's the mouse? Alrighty, sorry about that. For those of you at home, I just knocked over my cup of coffee and spilled 2/3 of it on the floor. So, anyhow, we just use the word stream. A couple other qualifications. It's got to flow. Okay, and in case you're wondering about that wonderful canal system we have, it can't be man-made either. So, Mother Nature must dig it. It's got to flow. And we don't care what size it is. So, it really does get down to, these are just low spots that water flows to. If you back up enough and look at a perspective, you could start to see how the water drains. Living in your house or your neighborhood for a while, or even your town, you might start to become familiar with places where when it rains a lot, the water flows. Okay? And, whether it's paved or not, you get an idea of how things move. Well, when we back up even farther and perhaps get the top of a high hill or a mountain or even an airplane or satellite, well, we get an even bigger and different picture. and we start talking about drainage basins, okay? And in between basins, we have divides. You may have noticed there's a few places along Route 90 there, the thruway, where they talk about entering different, and another word is watersheds, right? We've seen those signs. So, but heading towards Albany, heading towards Massachusetts, you'll see as we leave, it's the highest point on 90, and quickly thereafter, you'll see another sign that talks about how we're entering a different drainage basin. Okay, so just like the roof of your house, if you're standing on the sidewalk, staring at your house while it's raining, all the water to just the left of the peak of your house is going to flow what way? Well, it's going to flow to the left, of course, because that's a big old slope there. All the water that falls just to the other side of that is going to fall and run down the right side of your house. Mother Nature has the same sort of thing, and typically it's mountains or mountain ranges, but not always. It could just be, rolling hills that you don't even necessarily notice you're in a higher elevation at first. So another thing we see, and we're going to be talking about this a bit more later, is that oftentimes you'll have several areas that start to drain that lead to bigger and bigger and bigger streams. Okay, small ones feed large ones quite typically. This is a diagram of some of the more major basins around and the divides that separate them. You may have heard of the Continental Divide. All right, more or less the Rocky Mountains there. Separates the large inland basin there. Not really worried about the names of any of these, just showing you there the lovely taupe color in the middle. And then everything to the west of that Continental Divide drains in the other direction there. We've got one, not exactly on the Mississippi, but again, sort of paralleling the Appalachian Mountains there for the most part. And everything that flows to one side of it, again, flows to the east. Everything else feeds into that large inland one there. And then, of course, the arrows showing you the direction of flow within those basins. Most everything over here flows out the Chesapeake Way. Okay, not everything, of course. You guys living where you do, you're familiar with your Thousand Islands there, the St. Lawrence Seaway. Okay, but for the most part, we've got everything draining out over here to the east coast. And up north, further north of us, everything drains to the Hudson, and so on and so forth. So, all right, so I was talking about how smaller streams feed bigger streams. And again, this is totally a matter of scale. One of the things, and I didn't necessarily hear it with you guys, but one of the things when we look at the topo map is, hey, how come that creek down at the end of my street isn't on the map? It's just not big enough. It didn't make the cut. All right, that happens a lot. Or it's not even like I don't want to say a real creek, but sometimes they're just ditches, and again, the local folks probably have names for them. But at the state level, they don't make it onto the map. Or if you zoom in far enough on, Apple Maps or Google Maps or whatever, a name might finally pop up. But at the scale of our topo maps. So that's sort of what's going on here. You might see, for instance, the lower picture on any given map. But as you zoom in, you'll see that what is just a little simple fork there is fed by dozens and dozens and dozens of other streamlets, if you would. All right. Anyhow, we call these tributaries because they contribute to the main water system, which we're going to eventually call the trunk stream, the main stream. Okay, around here it might be the Mohawk. All right. So there's a whole bunch of different streams that feed the Mohawk River, and there's smaller streams that feed those streams, and oftentimes smaller streams that feed those streams. So that's all they're trying to show you here with that little enlargement. All right, so I used to draw this picture on the board, and since we've gone all digital over the last couple of years, we're just going to use this nice little image that I borrowed from the USGS, Geological Survey. So what we want to look at here is the channel there in the center, the stream channel. Probably heard that word before. And that is indeed our first vocabulary word. The channel is the ditch that the water's running through. All right. At the very bottom of that channel, we have the stream bed, also a word you've probably heard of. And along the sides, we have the banks. So we've got the stream channel, which is composed of the stream bed and the stream banks. Okay, you got a bank on either side. A lot of people like to say they're standing on the stream bank. Many people, I should say, probably not a lot, but many people, unless your feet are wet, you are not on the banks, okay? You're probably up on the side, your lawn chair, your cooler, your tackle box, whatever. You are on the floodplain. All right, when it comes up and over the channel, you're on the floodplain. You've left the channel at that point. And those are the broad, flat areas. Oftentimes on both sides of the stream, sometimes just on one, it depends. A lot of factors that go into this. But the floodplains are the flat areas, and they are that because what happens is when the stream comes up, okay, and during a flood, there's a connection there maybe, it brings a lot of sediment with it. And you've heard that a handful of times throughout the semester, how streams carry sediment. And we even talked a little bit, I think, during weathering and erosion about how that is linked to the velocity of the water. So it's flowing hard, it's fast. There might even be more water in there than usual. It's carrying all kinds of sediment. So it goes up and over the banks, and what happens, you'll actually see the math for this a little later, the water slows down really, really quick as soon as it overflows the banks. And all that sediment it's been carrying, it drops. Now, while in the long run that could lead to a rocky mess all over the place, for a very long while, it actually serves to flatten out the area, because again, stuff flows to the lowest areas. So it starts to fill in all the low spots all around the stream with sediment and whatnot every time it floods. So you end up with this plain, this large flat area. So floodplains are actually created by the streams. And on the last thing we have here, of course, are the levees. All right, you've probably heard of a levee. There's a couple songs about levees. We seem to like levees. They do a really kind of important job. All right. What happens? Remember, I just told you that when the stream comes up and over, it slows down. Because it slows down, it can't carry all that sediment it's been carrying. Well, right there, right at the edge of the stream, is where it drops a lot of the stuff, the big stuff. And it builds up a little faster than the rest of the plain does. So it actually makes sort of a lump, a ridge along the stream banks. And that ridge is the levee. Now, because we love to live alongside of streams, whether they're picturesque or years gone by, we needed them for commerce. All right. Boats came along them, and then we went and built train tracks right next to them because, well, the floodplains are nice and flat and easy to build on. Never mind the fact that they flood. A whole lot of reasons we built there. We tend to come along and we enhance these levees, because you might go into a town or even maybe your town, and you're going to look at, now that we've talked about what a levee is, you're going to look and say, oh my God, how in the world did that stream ever build that levee? That's huge. Well, it didn't. More than likely, at some point in time, the township went in, the city went in, and they enhanced that levee. one town. I think it was the next town over from where we lived one time, because we wouldn't go by it all the time, but with some frequency. And as you're cutting through town, you go over this bridge, and you kind of can see a cross section if you look out one of the windows and sort of see the downtown area. They had a levee built up. I swear the dang thing was as high as the first floor of all the downtown sort of buildings and stuff. And they were right on it. I totally understand why they built that sucker up. But that was in no way, natural. So, anyhow, so again, stream channel. You got the stream bed, the stream banks, the levee, and then the floodplain. The neat thing about levees is they actually sort of serve as a natural flood control, if you would, okay? Because they actually sort of hyphen the sides of your banks and could help to keep the stream in place, in check, in future years. The only other thing worth note here is this abandoned floodplain, and that's not a vocabulary word or even the word terrace there, but it serves as a reminder that streams are erosional and weathering devices, and they cut into the earth so many times. And I even know what's going on, and I do this myself. I look at a stream and I look at the valley that it's carved out and say, oh, how did this silly little stream ever carve this valley? All right, and at some point in its past, it was bigger, it was broader. And you know that because you know how streams work now. Okay, you know, and you will learn as we go through here, that as it's weaving its way through here, it's removing sediment, it's cutting down into the earth, and they did carve, those valleys. Mind you, it was a low spot to begin with, or the stream wouldn't have been there. But they carve it out and carve it out and carve it out. Just sort of a reminder, if you would, of the vocabulary we just talked about. Just a little cartoon that shows some of the, illustrates what we were just talking about, really. We have your stream up there in the first drawing, just on a normal day, okay? And then a massive flood. They've seriously exaggerated here. But we have this massive flood of the valley. And you can tell right here where they've deposited some new sediment, okay? Again, this is drastically exaggerated in its flooding here, but and then as it goes back to its normal river levels, we have then these lovely deposits here, the levees. And as I said, in the future, then the stream will be that much harder for the stream to flood, especially if it's something that doesn't happen, yearly or seasonally. And this gets an opportunity to get vegetated and compressed, compacted, whatever you want to say. All that stuff is as well. It makes it just that much harder to wear away the next time. But flowing water is really strong, as you're probably aware. All right, another view and a lot more vocabulary. I'm going to try. One of the things I was doing before class here was in changing these slides into sort of a widescreen format. This picture can certainly benefit from being a little bigger. Definitely need to change that font color though now. And we're not so much concerned about this picture over on the side. So there we go. All right. So again, we're taking a slightly different perspective here, and we're looking at the stream from up above. And we're going to start up at the top. Streams flow downhill, okay? So what we have at the very top of the stream we call the headwaters. The headwaters, that's where way up in that drainage basin we start to collect all the various water. And this could be multiple streams feeding into one. We could just be talking about a single stream. It totally varies. But, suffice it to say, the headwaters are where the stream begins. Coming down next, we see tributaries. Okay, remember we talked about tributaries already? Tributaries are these feeder streams, the smaller streams that are going to perhaps feed a larger stream one day. So then we jump down and we see the trunk stream. The trunk stream is that main stream channel that we're feeding. And then around here again, we gave you the example of the Mohawk. All right. So we're coming down. Again, scale on here is not even attempted to be mentioned, but this is, a regional view. In outline there, we sort of see the drainage basin. So then we come down, and it's not a term that we use, but you see how it gets a little, braided there. Okay, a braided stream is a thing. I felt we had enough vocabulary, so I don't hold you responsible for that one. But oftentimes, if the stream will break into a handful of shallow, narrow little streams that sort of trickle all over the place and then come back together. And again, wandering around, you'll perhaps notice this in life. Before we get to meander, I want to add one term that isn't on here. And that is a distributary. Remember, we had tributaries that feed the streams. Now we're going to add a distributary. And if you couldn't have guessed, distributary removes water from the stream system. Distribute, right? And this is really just a function of topography, a lay of the land when it does happen. Every so often, a stream will branch out and it'll just go downhill somewhere else and do its own thing. Okay, well, the rest of the stream keeps flowing. So that is a distributary and not on here. Next, we've got meanders. Meanders kind of get their own slide, but those are bends in the stream. And again, we tend to see those when we're farther along down in the plains. The streams come out of the higher parts of the basin. And things level out, and it starts to just do the day-to-day grind that streams do. Meandering increases as a stream gets older. All right, it's because of how they wear away the land that meanders form in general. So we'll talk more about meanders in a bit, but those are bends in a stream. Got floodplain. We already talked about floodplain. Then we've got the delta. You've heard of river deltas, be it the Nile or the Mississippi, or there's a handful of others. The delta forms right where a stream is joining a large body of water, typically. A delta is a deposit, which means it's formed by the river depositing sediment. It's also named after the letter delta, the triangle D. Okay, they often look shaped like that. That's why we call them that. And it's kind of neat how they form. You got to pick one of those many little streamlets on there. Usually helps to start on the left or the right side, but it could have been any of them in reality. And so streams carry sediment, I should say. And then as the velocity decreases, we talked about this several times, that sediment gets dropped out of suspension. So really this stream has been depositing sediment probably for some time now. As it's getting into flatter and flatter areas, it loses its motivation, so to speak. And it stops being able to carry a lot of the big stuff it took out of the area before it. So it's flowing down, and it hits a body of water be it an ocean or a bay or a lake, whatever, even if there's waves going on there, for that stream, that's essentially like hitting a brick wall. All right? It just slows it down so fast. And as such, it drops whatever last little bit of sediment it's been carrying. Makes a deposit, grows a little land, whatever you want to say. Well, at some point, it sort of chokes itself off. It fills up so much with sediment, okay, that it can't flow anymore. So it backs up, floods a little bit, if you would, until it finds another low area, and then it starts channelizing through there. And over time, you start forming that next little streamlet there. But the same thing eventually happens. This takes thousands and thousands of years to form, usually. Okay? These are not an instant thing. I typically use, and I will right now, the example of one of those sprinklers, broadcast sprinklers that you see in the backyard. They go very slowly across your yard, then it goes all the way back and starts over again. Okay. Well, imagine that if it, took thousands of years to form, but eventually it covers that whole area. And a little bit of water still trickles through the old channels. It doesn't completely kill itself. Sometimes it does. This is drawn for educational purposes, of course. So we want to keep it, looking as cool as they can. But yeah, there's any given reason that one streamlet could stay and another one clogs up. They're just trying to show you, the reason for the width. So that's a delta. Also, as you can imagine, and you probably learned in one of your civ classes or history classes, that these are really, really fertile areas. We love to farm them, so on and so forth. Again, you think about all the sediment that's been coming down there, also organic material too. All right, and so this does end up being some fairly rich land. Just really wet too. Last but not least, we've got the term mouth there. Okay, the mouth is where the stream flows out at. It's the stream end. So we have the headwaters for the beginning of the stream. We have the mouth for the end of the stream. It doesn't really sound like they've traveled very far from the head to the mouth. I don't know. They just didn't want to call it the foot or the tail. I don't know why, but at any rate, they went with the stream mouth. I guess because it pours forth, right? So the mouth of the stream there is the end. And just to touch back on something we did talk about down in Louisiana, there with the Mississippi River and forming that famous delta down there, we constantly have the wave action wearing away at these deltas. But the indication here, since they actually did grow, is that you have way more sediment coming downstream than the oceans could ever ponder removing. Okay, that is until we get in the middle and start screwing around, and we slow down the amount of sediment coming down said stream, and we stop that delta from being built up so much, and then the waves can take it away. Again, just a handful list of terms. I'll give you a second to make sure you got all those. Maybe we'll get a little more paper towel. So we have stream anatomy as it applies to a cross-section of the channel, and then we have stream anatomy as it applies to running along the stream itself. Okay? You guys have any questions about any of the terminology, when or where to apply it, when not, etc.? Okay. Cool.
what a mess. All right, so meandering. As I said, meandering increases with age. So you can kind of really tell how old a stream is by how meandering it is. It's sort of that old allegory about a young person will walk straight and true kind of thing, and an old person meanders around. I think somewhere in there is a little of both, right? We walk in various ways throughout life, I suppose. But that's the generalization that they use. So the older it is, the more curving you'll see. Again, it boils down to math, why it happens. All right, differential weathering and or erosion. What really essentially happens is the outside of a curve, a bend in the stream, weathers faster than the inside. And more so, we also get a deposit on the inside of a bend instead of weathering. We'll show you a picture of what's going on here in a second, but just to work with that for a minute. So, again, picture a stream, any stream you've ever seen in your life, and there's a turn in it. We talk about the outside of it and the inside of it. Your elbow is a great example. Your actual bony elbow point would be sort of the outside of that turn. Your elbow pit, if you would be the inside, okay? And then we need to talk about water. Remind you that water loves to stick together. And we have to have a silly little image of a stream that's flowing actually being bands of water molecules. Stripes, like army men marching into some horrible battle. Okay, just row after row after row of water droplets going down that stream. Any of you do marching band? Be brave, raise your hand. I was in orchestra. We can admit these things now that we're past them. We got one marching bander. All right. What else do we throw out there? NASCAR folks, racing folks, horse racing. No, the rest of you just don't march and you don't watch cars. All right. Well, you just have to pretend you understand what we're talking about then, because cool kids are going to talk now. So we'll go back to the marching band thing for a minute. So, I don't know, did you guys spell cool little letters and march and make neat little designs and all that stuff, or did you just kind of stand there and...
We tried, but we didn't have enough people.
You didn't have enough people, okay.
But
all right.
We did like the warm-ups, if that makes sense.
Yeah, all right.
Lines, but like on the turf. But
okay.
It was like 30 kids, so it never looked
okay.
good.
I came from what I thought was a fairly big school till I met Proctor, and good Lord, that's huge. But we had a good-sized school. We probably had 200 kids in our marching band. So they did all kind of cool crap. And maybe you guys have watched football and you've seen these bands during halftime. Most people wander off when the band plays. I get it. So you've got this whole line of people. And again, they're making a turn. They're going to spell out Washington Mills or wherever they happen to live, right? So they're walking around. They're spinning around. And... you've got maybe 25 people long, even if you only have 30 people in your band, maybe you got 10 people in that line. What do the people way out there on the end got to do if they want to keep up with the person that's, say, the pivoting? Can they all walk the same speed? Somebody's got to speed up, right? Because they've got to cover... Go ahead.
It's like the same way like if you're running track.
Oh, I could throw track into this. Go ahead, please. Okay.
Sideline, like you start first, and like the one on the outside, like it's along further on the track, like the starting point.
Is that when they stagger?
Yeah, that's why.
Okay.
If you're running on the outside, you're running more.
You're running more, and this is where I usually use race cars. But thank you. Yeah, I could definitely use track for that. So think about race cars. All right, if you didn't run track, the outside loop is who's got the easier ride here? If you're on the inside loop or the outside loop?
I definitely the inside. Yeah,
you want to be inside, right? It's a shorter trek. It's a smaller circle. Okay. The guy on the outside has to run a whole lot faster or has to drive a whole lot faster to keep up with the guy on the inside. You can use any kind of metaphor you want, analogy. One of these days I got to figure out the difference between those two. But we've got a handful of you now thinking what we're thinking about here. All right? Well, water does the same thing. It doesn't think about it, though. It just does it because, remember, it loves to stick together. All those little bands of water molecules love to stick together. So as the water's going around the curve, that water way on the outside speeds up. And the water on the inside of that bend, it slows down. Right? Now think about what we learned with weathering and erosion. The faster you go, the more stuff you can carry. The slower you go, the less stuff you can carry. And sometimes you got to just drop stuff because you just don't have that energy anymore. So every time that stream goes around the bend, it eats out, it digs out on the outside part of the bend, and it drops some sediment on the inside. That's what we mean by differential weathering and erosion. Okay? The inside of the curve weathers, the inside deposits, and what that does over time is it doesn't widen the stream, but it moves it. You tend to get, and I don't know the math on this one, but you tend to get equal sort of digging out on one side as you get depositing on the other. Okay? And what that does is it takes, we're going to look at the middle here of each of these. It takes this normal bend and it brings them, see how it's starting to pinch together in the middle there, it brings them closer to one another. So that's what we mean by meandering increases with age. It takes time to do that. Okay? So the more of those you have, it's just accentuating a natural bend. That's all it's doing. Now this slide is talking about something we call oxbows. Because everyone knows what an oxbow is. Even if they use a slightly more modern term like yoke, still, half the people on the planet wouldn't know what a yoke was. But we used to use oxen to plow fields, etc., haul carts. And there was this, you've seen it in movies, there was this big old wooden horseshoe-looking thing that they put over the ox's shoulders, attach the cart to it. That's an oxbow. Also, again, a yoke. So, these things tend to look like, for the geologists of old, giant oxbows. And you'll see some pictures in a second, real pictures. All right. So oxbow or an oxbow lake is a cutoff meander. Because again, let's think about this here. We're getting closer and closer. We're bringing these meanders together. At some point, they are likely to join. Again, this is hundreds, if not thousands of years. Hundreds will probably work. And water, like everything else on the planet, follows a path of least resistance. So again, not that it cares, not that it wants to, but we talk about it that way. It's a whole hell of a lot easier for that water to just keep flowing straight at this point than it is for it to go all the way around that bend, all the way around the other bend, come back in. It's just easier, so it goes straight. And it starts digging out that channel. And what happens is that old meander gets cut off. And that's where they call it an oxbow. So looking at this one, all right, you can see that we have one cutoff meander already, one oxbow there, and you could probably pick a couple that are going to be next. That one in the top back certainly looks like it's ready to go. And then the one in front of that may be next. So the neat thing about this is, if you follow this out long enough, you will cut off all of your meanders and you'll have a straight stream again. So they start out straight and narrow, and then they wander around the meander through as they get older, and then it tends to straighten itself back out again. And the neat thing about these oxbows, again, if you spend a lot of time, whether you hunt or just hike or whatever you do, you might have come across these. You can't tell from on the ground unless you're paying a lot of attention. It's going to look like a stream, but it's probably not flowing. All right, and then it'll just disappear or it'll just appear depending which way you're coming in. And they're there. You think about where these things are for them to maintain themselves. You're probably in an area that has a decent amount of precipitation, and they're lakes. Sometimes they swamp in if you're in a really wet area. towards the back part of that bow there. There's a lot of different ways these can go, but this is, again, set up to be a really useful slide, so they took a very purposeful picture. So meandering and oxbows, and track and marching band and race cars. And now, if you didn't know why you want the inside track, now you know why. But that's awesome that they stagger them when they're racing. That way it's fair for everybody. I could say they could just put the faster people on the outside and make them work for it, but or there you go. Kind of dog it the whole time and then come in on the race and win. But yeah, that's great. Yeah, it's super simple. I never thought about why they staggered that. All right, moving along. Stream flow. So again, you've seen rivers, right? Hopefully. Sometimes they're roaring. Sometimes they're barely flowing. And sometimes a stream that you know is really slow or really fast, you walk by it on a different day and it's completely different. All right. So we've got absolutely no reason or purpose to talk about, to memorize, I should say, how fast a stream can flow. It varies incredibly. All right. And not just from season to season, but even if we went down to Proctor Park now and walked along Starch Factory Creek, you're going to find some areas that are flowing really fast, and you go 100 yards down, and then again, it's barely moving. So it'd be much more helpful and interesting, I think, to talk about why those variations happen than to memorize that the fastest stream on the planet is this one, and the slowest stream on the planet is meaningless. So we're going to talk about what affects stream flow for a little while. So there's three fairly straightforward things. The first one you learn as a toddler. Not necessarily about streams, but that slopes are fun. Whether you're going to roll down that hill as a little kid, or more than likely your little toy cars, okay? And you want to make them zoom, zoom, and you realize pretty quick that if you put them on a slanty thing, that car is going to go a lot faster. So that's gradient, slope. We tend to use the word slope when we're going uphill, and we use the word gradient when we're going down. Same idea. Same formulas, I'm pretty sure. And don't worry, we won't be calculating slope or gradient. But we're really talking about how steep it is. Okay? The next thing is the stream channel shape. And we've got some pictures to talk about that one. But suffice it to say that certain shaped streams flow differently than others. Well, I don't even want to, like I said, touch on it too much. And then discharge. Wonderful word, discharge. In most of our minds, it's something really negative. You're talking about discharge, gross. But all we're talking about here is the amount of water coming out of the stream. All right. As you'll see in a moment, it's usually some volume per time. Gallons per minute, liters per second. Again, it varies on what you're measuring. So discharge is the amount of water that comes through. And again, that has an effect on how it all works. All right, so let's look at some of these. So as I said, gradient is similar to slope, and you know and now can apply the fact that an increased gradient equals an increased velocity, okay? Steeper it is, faster it's going to flow. Simple. Good? Good. All right, channel shape. Channel shape, as I said, is a bit more obscure. And this is really evident, again, when you walk along a stream for a while and you realize how the channel does change. For one thing, we've got to keep in mind, regardless of how these are drawn, the scale of how these are drawn, we have essentially the same amount of water in all three of these pictures. Okay? That's a given kind of thing we don't want to vary for the moment. So we have narrow and deep versus wide and shallow at first. All right, so narrow and deep is the top picture. Wide and shallow is the middle picture. A and B, if you can see the A and the B there. We're going to tell you that narrow and deep runs faster than shallow and wide. All right. It's about friction, surface area. Narrow and deep, you have less water in contact with rock than you do in shallow and wide. So we're keeping the amount of water the same. We're just spreading it out over more area. And you will see a little math in a bit that actually goes a long way to explaining this. So again, if you're walking along a stream and it's flowing pretty well, and then all of a sudden you get to a spot where it just slows down. All right, unless you just came down a big hill, which was the first example. You probably didn't. Unless you just came down a big hill, take a moment and look and see if the stream is wider where it's nice and slow, as opposed to just back upstream there where you were, where it was flowing a lot faster. More than likely, it is. And not only that, it's probably shallower as well. That arrangement just tends to slow things down. So narrow and deep versus wide and shallow. Narrow and deep is going to be faster. Now we want to look at the top picture and the bottom picture. A and C. Narrow and deep, but the bottom one is full of rocks. Smooth versus rocky. Again, it boils down to surface area. Not going to have you get a ruler and measure all these little crenulations here in the rocks, but suffice it to say, you've got a whole lot more surface area with those rocks in the way than you do in the top picture. So that's just a bit more friction. It is supposed to slow things down. All right, it's supposed to slow things down. Now, for a handful of you, this is hopefully raising a little red flag or at least a question mark in your head. If you canoe or kayak or paddleboard or any such thing, you might be saying, wait a minute, there's these things called rapids, and they tend to have a whole lot of rocks in the way, and those are really fun because the water's faster, and there's that rock that we might smash into, and that's sort of exciting a little bit. And. So if in this picture we tell you that rocks slow down the water, well, why do rapids, which are rocks in the water, right? Why are they faster? Well, we'll come back to that question. You could ponder it while we're talking if you like. You don't perhaps have all of the tools necessary to answer that question yet. All right, and the last one, discharge. So as we said, discharge is really just the quantity of water, and it's measured in volume and time. Gallons per minute is a really common one. We use that in our houses typically. Okay. Cubic feet per second is a sort of real-world application if you're out there measuring an actual stream. Gallons per minute is a bit small. So they might talk about cubic feet per second. When we talk about gallons per minute, I like to try and actually picture these milk jugs going down the stream as a measure of such thing. And it makes it a little easier to picture. So we're going to tell you that we're finally to that math, okay? And we've got a formula. It's a simple formula. There is no math requirement for this class. We've done a little bit of mathing here or there. Tried to keep it fairly simple. So now we just have a little bit of algebra. And we have the formula Q equals VA. Q is the quantity of water. way back when I started learning this, I don't know why we didn't use D, for discharge. We keep talking about discharge. Let's call it discharge. Well, Q works just as well if you remember that it stands for quantity. So, the quantity of water that's flowing through a stream is equal to, we're just reading the equation now, the velocity of that water, and A's area, so the area or the size of that channel. Well, that makes sense, right? The amount of water that can flow through a stream is equal to, or a function of, say a function of, right? How big the stream channel is, and how fast the water is flowing. I'll give you an example in a second. We are not Mother Nature. Most of us cannot do differential equations and all that fun stuff. Some of you can. God bless you. I can't. We like to keep things very simple. Me personally, I could barely handle one variable at a time. All right? So you do part of the equation, then you change something else, then you change something else, then you change something else. Mother Nature's not bothered with math. Math is our attempts at understanding what the hell she's doing. Calculus. Most math is true. I don't say true. Real is a harsh word as well. You have 5 apples, Susie takes 2 of them, you have 3 left. That's easy to see. Okay? But when you move into calc, it becomes a bit more obscure for many of us. So we're going to keep it a nice, simple algebraic equation, and it remains algebra because we're only changing one variable at a time. So, picture, if you would, if you can, you got 2 streams side by side for some strange reason. I don't know why. But you got 2 streams. And you've got what are we doing here? Okay, we're doing channel size first. So you have a big channel on your left, and you got a small channel on your right. Again, for some strange reason, they're flowing at the same rate. And they also have an unlimited amount of water to keep them filling. Which one's going to have more water flow by you in, remember we need time here, in 5 minutes? The wide one. How come? Yeah, it's that simple, guys, okay? It's bigger. You have an unlimited amount of water and a bigger area for it to go through, and you're forcing them to stay the same speed, you're going to get more water through in the bigger one. Same idea with highways. Cars are a little easier to understand. There's that stretch where and they have the same amount of roads, so the lanes, so it doesn't really help. But there's that stretch of, I want to say it's 69, heading out towards Rome, that parallels the thruway, right? So you've got, in this case we're varying the speed, but it's the same idea. You've got two lanes going this way at 65, and you got 2 lanes going this way at, I think it might be supposed to be 55. All right. Again, given an unlimited supply of cars, in an hour, which one's going to get more cars through? The one where you can go 65, right? It can go faster, more cars can get through, so on and so forth. Same idea. All right, and then I just switch gears here for the next slide. Same thing can be said if you keep the same channel size, but you have different flow rates. Same thing can be said. The faster one is going to get more water through. We just switch to highways and cars. I will never ask you to manipulate more than one variable at a time. If I ask you such a question, it'll only be just like we talked about here. But again, Mother Nature is not bothered by such things. Keep the math simple. I won't ever give you numbers either. Many of you can do this without numbers in your head. You understand ratios, proportions, whatever you want to call them, ratios. If you do need to do math, Keep it simple. Q equals VA. 25 equals 5 times 5. Just make up something. Could be 36 equals 6 times 6. It could be 50 equals 10 times 5. I don't care. But start with some numbers that you know. So, what we're seeing here mathematically is an example of the question, what happens to the velocity of the stream as the area of the channel decreases? So, time 1, if you would, your original stream, whatever you want to call it, is that 25 equals 5 times 5. That's a true equation. We understand it. We know it. We love it. So then we're going to say, what happens if the velocity? What happens to the velocity, which is v, if the area goes down? So you see how we changed a to 3 instead of 5. We want to know what happens to v. So now this becomes as simple as, how do you solve for v here? You divide both sides by 3 to leave yourself a v there. And as he said, it becomes 25 divided by 3. So to answer the question, what happens to your velocity as the channel size decreases? The velocity does what? Does it increase or decrease, you guys? It increases. I can ask you the opposite. If we increase the size of the channel, A gets bigger. A goes up to 8 instead of going down to 3. Well, we probably figured out at this point that V's got to give, right? Again, because you're still keeping that 25 the same. We're only moving one variable. And that's what I mean about ratios of proportions, okay? In order to keep this one thing the same, if you increase this, you've got to decrease that, or vice versa. So again, if you can't picture that in your head, please just throw some numbers in, little scratch paper on the side, right on the test. You know, I don't care about that. So that's how you do that. And this, my friends, you learned in lab class, whether you knew it or not. Because what happened when you turned that damn sink on? It shot everywhere, didn't it? Believe it or not, that's on purpose. Not to turn lab class into a wet t-shirt contest or anything like that. That's not why they did that. They put that 3-inch nipple on the end because they want you to be able to hook a hose or tube up to it in order to run water. Maybe in a chemistry class they've run water. I don't know. But that's why they're there. I've never had a reason to do so. Think about it. That water's been traveling along through all the pipes for however long it's flowing, all through this building, coming along. You turn on the faucet, it comes through, comes up, comes around. And then in the last 2.5 inches of its journey, it goes from like a big old Sharpie marker down to something you can't even fit your pencil tip in. Not only does it change its diameter drastically, but it does it in a very short time. It jacks up that velocity like crazy. And again, the idea is so you can give it some velocity to flow through a tube to get to further down the table or so on and so forth. Maybe to help you rinse out your beakers, but we don't want that stuff going down the drains anyhow, so I think it's the tube thing. And again, it's tapered so you can slide on the rubber tubes. So that's why the lab sinks get you wet. Another application. Again, if you don't have this situation, you may have driven by, or someone you know has this situation. You get out of the city, typically, and sometimes in the cities, and you've got a ditch between the road and your house. Okay? And that ditch, of course, is there because it's draining water. But you've got driveways. And unfortunately, we don't have drawbridges anymore. I think it would be a lot cooler if we still had drawbridges. Although now as a homeowner, I'd have to maintain that drawbridge, so I wouldn't be so thrilled about it, I suppose. But because we don't have drawbridges to go up and down, we put a big old pipe underneath our driveway, right? And then we pave over it, and that's your little section of pipe there. Culvert, I think we call them sometimes. Well, you're coming from this ditch, and think about all the stuff we just learned. All right, you're coming, ditches are full of rocks, ditches are uneven, ditches are fairly wide. Then you're coming into this nice super smooth pipe for 10, 15 feet, however long your driveway is. That's like a water slide for the water. Fun. Speeds up. Well, what else did we learn? If it speeds up, it's going to dig out on the other side because the water's moving faster. It moves sediment. Look on the downslope side. If you have one of these, or again, if you're driving around, don't get hit by traffic, please. But look, go slow, and you'll see on the downstream side of these driveway pipes that it's going to be dug out a whole lot more than it is on the upstream side because the water speeds up in that smooth pipe. For once, took us 14 weeks to get here, but real world application, right? All right, we're coming up on running out of time here, but I do want to get through a handful of more things. Competence and capacity. We've been talking about this the entire time. Competence and capacity are two words we use to discuss erosion in a stream. Remember, erosion is movement. All right? Competence is the largest sediment size capable of being transported in a stream. But how competent is it? How big of a piece of rock can it carry? Remember our rock sizes: boulder, cobble, pebble, sand, silt, clay. Right? We got a comprehensive final in here. We don't want to forget things like that. This is what it refers to. On any given day, a stream is definitely carrying silts and clays. It's super light stuff, right? And probably it would move sand along without any problem. Pebbles, that's where we start to get a little questionable. Cobbles, even more so. So you would say the stream's competence gets you to, roughly sand-sized grains. Now, if you put a whole lot of water in, let's say you had a heavy rain, and we didn't really go through that equation a whole lot, but if you increase Q and keep A the same application, right? Something's got to give. So if you're increasing Q, you're keeping A static, V is going to go up. Once you increase your velocity, you're increasing that stream's energy, you can move bigger and bigger stuff. That's why flooding is so bad. Flood damage is so bad. It can really destroy, and I don't mean your stuff getting wet. I'm talking about to nature, okay? Once that water level starts moving up and moving faster, you can do a lot more stuff. Capacity is just think of like a dump truck. How much can it hold? All right. That is connected to velocity and whatnot, don't get me wrong. It's also connected to the size of the stream. We don't worry so much about capacity. But competence really ties into what we've been talking about. Because it ties into velocity and that whether or not you could pick up certain size things or whether you have to drop certain size things. But capacity is important too. So capacity is the total load. Competence is any given size of grain. And as we just said, these are linked to velocity. All right, we just have a couple more vocabulary words and we'll be done with this. Still talking about erosion because we're talking about transportation. Okay? We've got dissolved load, bed load, and suspended load for this moment. Dissolved, bed, and suspended. Dissolved load is just that. It's whatever happens to be dissolved in the water. The biggest thing is you probably never thought of this as erosion. We've spent all semester just referencing randomly, stuff that is dissolved in water. You turn it on, oh, you got egg water, sulfur water. Or you might have iron deposits in your sink or calcite, hard water. Well, that calcite or iron or sulfur had to be dissolved out of somewhere at some point. So from point A where it's dissolved to point B where it's landing in your sink is erosion. It's transportation. It was weathered out. It was deposited. But between those 2 points, that's erosion. So dissolved load is just that. Whatever happens to be dissolved in it. And that's not even a sediment size. Okay. Suspended load is whatever is floating along in the water column. This is at least referenced. I don't know that I've ever seen a teacher do this, but an age-old example we give you guys. You've all, again, hopefully gone by a stream right after a big rain, and you're like, oh my God, the stream doesn't usually look that brown and murky. All right? And there's all kind of sediment washing down it, so on and so forth. So, if you were to take a cup of that water, big old beaker full, and set it on the counter for 3 hours, well, that water's going to clear right up. Oh, you're going to get a nice little deposit of sediment on the bottom, silts and clays probably. That sediment was only floating along in the water column because the turbulence was keeping it suspended. The action, the motion, the energy was keeping it suspended. And it was a brown, murky mess, for sure, but not because stuff was dissolved into it. So you put it in that beaker, you set it on the counter, and it's removing that system energy. It's removing that turbulence, and it all settles out. So suspended load, we tend to see silts and clays as examples for what you can suspend. And that's why it looks so muddy. Remember, silts and clays, mudstone. And then we have bed load. Bed load is the heavier stuff. It's what it's lying along the stream bed. And I don't want you to worry about all these different words they have down there, sliding and rolling and no, right? Just keep it simple, all right? And you know that if that stream is flowing fast enough, it's going to be knocking around some of the bigger stuff on the bottom. At the very least, sand and pebbles. Again, at this point, you can figure out if it's flowing fast enough, sure, it can move something bigger, probably. But we're talking about on any given day, and if I were to ask you these questions, it is in that case. On any given day, a normal day, what would you usually find as suspended load? Silts and clays. Okay. We've got one little hybrid here, and it's called saltation, and it has absolutely nothing to do with salt. Saltation refers to sand grains. And the idea that streams, again, just do what they do, and if they're fast enough, they'll move whatever sediment they can. So saltation refers to sand grains that look like they're bouncing. Because what happens is the water's right on that line, whether or not it can carry sand. So it picks up a sand grain, it moves a suspended load, and it says, oh no, it's too heavy. And it drops it down. And then it picks it up again. It says, oh yeah, no, I can carry this, I can carry this. Oh no, I can't. I think they make an example out of this, and possibly why they even gave it a vocabulary word, purposely for teaching. So we can explain this whole velocity is so important thing. What grain size you can carry. All right. So again, saltation refers very specifically to sand-sized grains and the fact that they're fluctuating between suspended load and bed load. Okay. And it's where that velocity is really just sort of teetering there. Because on a normal day, you probably wouldn't be able to move sand floating along in the water column. it's too big. So just a bit of summarization. All right, bed loads, we're talking about pebble and sand. Suspended loads, silts and clays. Siltation is only sand. It's a hybrid of suspended and bed load. And dissolved load. Well, I happen to give you the exact same examples that are right on here, but it's stuff that is dissolved at one point and moved along in the water. All right. And again, this PowerPoint is online if you don't have a copy of it already. What we are getting rid of is the discussion about flooding. Okay, I just want to take 30 seconds to tell you what we're skipping, so to speak. Suffice it to say that, that guy didn't park their trailer there the night before. Those cars weren't put there the night before. The water moved them, and we've all seen that horrible footage of water moving things that it really shouldn't move on any given day, to use that word again. Flooding is an increase in Q. Okay? It's a whole lot more water in the stream. And think about it, we don't call it a flood until it leaves its channel, right? So as the water's getting higher and higher and higher, if you've lived near a stream, I didn't grow up. I spent the last 20 years by Sequoia Creek, like 1 block from it. So we kept an eye on streaming, especially when it rained and or when it melted. And you start to be able to tell, that water starts getting brown, it starts getting higher, you start seeing little white caps in there. You start to pay attention. Suffice it to say, it's moving a whole lot of more sediment there. We know that because when it comes up and over its banks, just like we talked about the levees forming, you get those flood deposits all over. A lot of times if you're walking through the woods, you see them as sticks pressed up against the trees, all that sticks and reeds and grass and stuff like that. Say, oh, that's a flood deposit. Or at least you can now impress your friends when you're walking through the woods. The water was up that high. We also know from the floods that they leave all kinds of sediment everywhere. The silts and clays, that mud. But adding that to this conversation now where we've been, that also means it could move crap that it doesn't usually move, like your neighbor's car or the trailer or whatever, because it has that much energy. All right? So that's what's going on with the flood. It's an increase in Q. Now, the absolute last thing, we asked you this rapids question. If rocks in the way of the stream are supposed to slow everything down, because increased surface area equals increased friction, yada, 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 why are rapids rapid?
Because the rock's too big for the stream to move it, so it has to form path around it. And it's the same principle as if when it's like curving around it, does it increase in velocity?
Anyone want to add to that, subtract from that? You want to repeat it so now that they're paying attention?
I'm not going to repeat it, but
So he's very close. He's got a good part of it at any rate. It's actually just not that simple. Okay. He said something about the rocks being too big to move. There's a lot of things going on here. Turbulence is one of them. He mentioned water flowing around the rocks. Okay, and a lot of times that's exactly what you're riding in your little kayak there. Also, we've split into possibly many different stream channels. Again, Mother Nature doesn't worry about running numbers. She just does what she wants to do. So we've got a little channel here, a little channel here, a little channel there. You recalculate everything. But a lot of it is indeed turbulence. Okay, and even if it's not a lot faster, there's a lot more random motion involved and perhaps a little bit of deception going on there. But yeah, so that's why rapids are rapid and also why a rocky stream should be slower than a smooth stream. All right, you guys.